So today is lecture 14. We're going to be discussing the Schrodinger wave equation. And as usual, we start with a review of the previous lecture. So what did we do in the previous lecture? We talked about the simple quantum harmonic oscillator. We used this trick of A and A dagger, lowering raising operators to solve the Schrodinger equation or solve the system or Heisenberg equation, depending on how you want to call it. Then what we found was that we found the energy eigenstates, right? So ket n and x prime. And ket n, these are energy eigenstates labeled by a positive integer, which is the eigenvalue of the number operator, namely A dagger A. Then using we assume the existence of a vacuum state. The vacuum state is the one that has a eigenvalue 0 for the number operator, which means that it's killed by the lowering operator. Then we systematically showed that A dagger to the power of n acting on this vacuum divided by square root of n factorial is a normalized eigenstate corresponding to ket n. So that's what the ket n is. And of course, this became we use this to write down the position space wave function for energy eigenstate ket n. And the way it looked like was that the vacuum state was Gaussian. There was a characteristic timescale x naught, if you remember. And this A dagger operator's action looks like this differential operator acting on x naught. And then the answer is there could be written in terms of Hermann polynomials, but this is a more elegant way of writing in one shot. All right, so what do these wave functions look like? Because they're all real, I can plot them easily. And this is what they look like. This is the ground state. This is the first excited state, second excited state, blah, blah, blah. Right? There were interesting properties of this. We saw that x, the expectation value of position operator, was 0. Even though we had, when we solve for, well, that's my next point. When we solve for the x operator as a function of time in the Heisenberg picture, it was evolving. We were showing this oscillatory motion in terms of time. Nonetheless, the expectation value of x is 0 at all times in all these states. Do you recall why? Because the expectation value of x naught and p naught were 0, right? So you got to be careful how you associate interpretations to these quantum equations. We saw that the A and A dagger act like oscillators rotating with frequency omega and minus omega in this complex plane. So this is how we integrated them. So often A and A dagger for this reason are called the positive and negative frequency modes. Right? So you hear those expressions a lot in physics. Any questions about this part? Then we said that another way of deriving this equation is using the so-called Baker-Campbell-Hausdorff BCH expansion. For you guys, view this as an identity for matrix algebras, for matrices, and an identity that is useful and is used all over the place in quantum mechanics. The reason, so what does the identity say? It says that if you take this exponentiated thing, e to the power of I g lambda a e to minus I g lambda, then you could expand it in terms of these nested commutators, right? Why is this nice? The reason is that in quantum mechanics, time evolution of the Heisenberg operator takes the form of this form. This is the operator. What was the interpretation of I commutator of G and A? If in time evolution, G is H Hamiltonian over H bar, or Hamiltonian, right? Then what's the interpretation of the first term in this expansion? What is the interpretation of this term? So the first term is I2 over H bar, the commutator of H and A. Have you seen this expression before? If I remove the T, have you seen this? Yes, this was the Heisenberg equation. So this was del T of A, right? So what's the next term? The next term is HA with two factors. We'll remove the T squared. So there's one IH bar, one IH over H bar. I'm going to put one IH bar here next to this guy. So that now this becomes the commutator. So it becomes all 1 over H bar, H del T of A. Del T of A. What is the interpretation of this from Heisenberg equation? The second time derivative of A. What is the interpretation of that 1 over 2 factorial? It's just Taylor expansions. So this is nothing but saying A of T is A0 plus T del T of A plus T squared over 2, second derivative of A, time derivative of A, and so on and so forth. Taylor expansion. It's nothing but that. Good? I didn't have time to go over this last time. So hopefully that helps the interpretation a little. Any questions? I could have, for a physicist, I could have proved this using this BCH, right? So if at any point you forget what BCH is, the expression is, it's just Taylor expansion of A of T as a function of, and for small t. Any questions? I don't know if you guys see down. Yeah, okay, you see that. All right. An interesting thing that we found, I said this earlier, is that if you look at the expectation value of x of t as a function in energy eigenstates, we kept them, call them stationary states. Why do we call them stationary? Because their time evolution is simply a phase, right? So this time evolution of ket n is ket n multiplied by e to the power of minus energy of ket n t over h bar. What was the energy of ket n? H bar omega n plus half, right? Because it's the evolution of it is a phase, you could immediately see that for observables end up being in the stationary state, their expectation values in the stationary state end up being time independent. As you expect here, you could check that explicitly. Good. So even though the physics as an operator x of t is showing this oscillatory behavior in energy eigenstates, the expectation values show no oscillations, right? So said differently, energy eigenstates are far from your classical intuition. Now, what are the states that show oscillatory behavior? Well, take any two, whoops. Take any state which is a superposition of two energy eigenstates. Now, by plugging this back into that equation in here and calculating the expectation value of x of t in this state, you can see the oscillations. Where do the oscillations come from? When I plug this, when I calculate x of t and this state plus z1 c11 c0 star plus 1 c1 star, there are four terms in this. There is a term that's 0 0 that shows no oscillatory behavior, right? It's time independent. We just said that. There's a term that's 1 1 that shows no oscillatory behavior. However, there are the cross terms 1 0 0 1. They show oscillations. What does this mean? It means that if you take the operator x of t in energy eigenbasis, the diagonal elements are time independent. The off diagonals evolve with time. Everyone is with me? Good. So that is one important lesson. I'm not gonna write the right hand side. I explained that it works. Good. So that is what the oscillations come from. Any questions? So we also said one more thing, which is, what is x of t? X of t in this energy eigenbasis is a tridiagonal matrix, right? A tridiagonal matrix, and its diagonal elements have to be 0. Why? Because it's just a sum of A and A dagger. A raises the ket n, sorry, lowers ket n. A dagger raises it. So you can't have a diagonal. We explicitly wrote down what the matrix elements are, right? So it's all off diagonal. So the only chance that you have for getting something out of x of t is that you have a superposition of ket n and ket n minus 1 or ket n plus 1. If you superpose ket 0 with ket a million, sorry, the energy eigen's in vacuum with some energy eigen's in 100, you're not going to get x of t out of that. You're going to get higher powers of x of t, the expectation value out of that, but not x of t. All right, is that clear? So it seems like the energy eigenkets are not behaving classically, right? These states show some oscillatory behavior, but now the question is, what states are there states in quantum mechanics at all that match your classical intuition of an oscillator that just keeps oscillating back and forth? Are there such states? The answer is yes. These states are very important in physics. They're called coherent states. I gave you a different definition, and unfortunately in this course we won't have time to prove that these two definitions are equivalent, but these are states that behave most classically. Of course, they're not fully classical because they're pure states, right? A pure state cannot be fully classical, but as pure states, they still behave very classically. What does it mean most classically? One simple way of quantifying is that they saturate the uncertainty relations, because uncertainty relations were lower bounds on your ability to simultaneously pin down incompatible observables, right? So you could, in these coherent states, you could measure incompatible observables as well as is allowed by nature, right? So here's another definition of them, and I absolutely encourage you guys to think about how is this definition equivalent to the other definition? Why is this telling you about minimum uncertainty? If you ever take a course in quantum optics, a third of your class is going to be about the fact that I just said. So these coherent states are eigenkets of the annihilation operator. Is the annihilation operator an observable? No, it's not, because it's not Hermitian. So a priori, it's not clear that you're going to have eigenkets or what the eigenvalue is. The eigenvalue need not be real, and generically it's not. So this number lambda is complex, right? This is the very first time in this class, or probably most of what you do in quantum mechanics, where you deal with eigenkets of non-Hermitian operators, but they play an important role in coherent states. So a very, very beautiful fact about them is that if you look at this, so what you could ask me, what do these eigenkets look like written in terms of the energy eigenbasis? All right, so take one of these. Oops, sorry. Oh. I did this poorly. I think this is going to be, yeah. Let me call this lambda. So what do these eigenkets look like? Look like coherent state kets look like with an energy eigenbasis. Well, of course, if you expand them, there will be a bunch of coefficients. If you're asking what these coefficients are, first of all, these numbers will have to, if you square them and sum them, they should add up to 1. So they look like up to phases, right? They look like a probability distribution, square of a probability distribution, up to phases, right? So what is that probability distribution? Is this? Do you recognize this? It's Poisson distribution. So just one lesson for you guys as scientists in general, no matter what field of science you're in. There are 2 distributions you should love. Gaussians, Poisson. And if you're very sophisticated, anything in between. What is the origin of Gaussians? Why do we see Gaussians in nature? Any idea? There's a law of nature, a law of probability theory you've heard about, probably. Law of large numbers. It justifies why Gaussians appear in nature. There's also another law of nature that tells you why Poisson appears in nature. Anyone has heard of that? Law of rare events. And those are the only 2 things that you have. Rare events, right? And for Poisson, and large numbers for Gaussian. Read about them. I don't have time to teach them. It's very, very simple. Intuitive. It's extremely intuitive. And it's perhaps one of the biggest insights that we have. Like one of the major insights that we have in sciences. All right. So these guys are Poisson. We already found Gaussians. What were the Gaussians? Where did you find Gaussians? Energy eigenkets, right? The vacuum ground, the position space wave function for the vacuum state was a Gaussian, right? Then the energy eigenkets higher modes were derivatives of that, right? So they're no longer Gaussian, but they're Gaussians with polynomials sitting in front of them. But the vacuum is always Gaussian. Good. Any questions? There's a lot of beautiful mathematics with rich physics going on here in coherent states, but unfortunately, we won't have time to cover this in detail because this is a general course in quantum mechanics. I'm just like discussing various examples of things that appear all over the place in physics. Quantum mechanics is basically taken over physics. It's everywhere. Any questions? All right. Remember the law of large events, Gaussians. Law of large numbers, Gaussian. Law of rare events, Poisson. All right, time-dependent wave function. Any questions? So this is the summary of the last lecture. I didn't get to coherent states, but I just covered it now. Yeah.
So maybe like kind of looking at these equations, it looks like there's sort of this circular logic, right? It seems like you need to know what lambda is.
Very good, very good. So thank you so much for pointing that out because it makes it matter. So this is the kit, right? It's a coherent state labeled by lambda. And this is how I wrote it. So you might ask me, your question is, what is lambda physically? Turns out, if you want to know what lambda is, calculate the expectation value of number operator in this kit. It will fix for you lambda in terms of n. That's what my n bar was in the previous equation. I just switched it because I realized I haven't defined what n bar is, and I left that for you guys to figure out what lambda is, right? Of course. Now, what is interesting is that these guys are labeled by lambda. Lambda is they're part of lambda squared, actually. The absolute lambda is a complex number, so this absolute value squared is controlling expectation value of number operator. And it's a continuous variable. You could continuously vary these. There's a lot of beautiful physics with coherent states. Anyway, any other questions? That was an important question. I hopefully it's clear that there's a phase here that I'm suppressing. All right. So this equation is not literally true. What is true? Well, you know that, right? So do I need to explain it? All right. Time-dependent wave equation. So recall what the wave function position space wave function is. It's the bracket of x prime and alpha of t naught t. That's the ket at time t, some ket at time t, and this is the position eigenbras, right? All right. So take the Hamiltonian to be p squared over 2m plus v of x. This is the Hamiltonian we work with in quantum mechanics, usually for a non-relativistic particle. V of x is, of course, diagonal in the x eigenbasis, right? That's obvious. And p squared, this was related to one of your homework. We saw that p is actually related to, could be up to I and h bar. It's just del x derivatives with respect to x. So p squared ends up being h bar minus h bar squared over 2m nabla squared. This is p squared over 2m. Right? So if my Schrodinger equation, time-dependent Schrodinger equation, was I h bar del t of the wave function is Hamiltonian insert in the middle, that means that the right-hand side could be written as minus h bar squared over 2m nabla squared of the wave function plus v of x, the wave function. Written in terms of the wave function, you get this equation, which is in many books in quantum mechanics, is the first page or the starting point. This is the time-dependent Schrodinger equation. So when quantum mechanics was discovered, Heisenberg discovered it in terms of matrices. Schrodinger later on, without understanding the connection to what Heisenberg had done, came up with another picture, which was in terms of these wave functions and this differential equation. It was only later that people realized that they were the same. Schrodinger had no idea. Heisenberg even didn't know about matrices. He invented this stuff. And yeah, well, he didn't know about the details of matrix algebras. All right. Is this clear? Now, what is the analog of calculation of energy eigenkets? For energy eigenkets, the time evolution is, the time evolution is, we said if the Hamiltonian is time independent, is simply the wave function is multiplied by e to minus I energy t over h bar, right? This is a stationary state. So these are equivalent sort of words I used. Stationary states, energy eigenkets, energy eigenstates, right? So this means that if you take this guy and plug it on the left-hand side, the time derivative, IH bar, will give you E prime. So this is the, maybe I should move this to the right side, left side, the other right. Right? So what I did was I replaced this as psi in this equation. And now we usually, sometimes we write the energy, at least in Sakurai, the notation for an energy eigenket wave position wave function is u of e of x prime. So it will have to satisfy this equation. This is the time independent wave equation or Schrodinger equation. Good? Any questions? So you see the advantage of this notation that Sakurai or Dirac invented, right? You don't have to, yeah. Questions? Because I'm no longer dealing with operators in these expressions. Operators are replaced by differential operators, right? In my notation, I don't need to care about x prime and x or anything like that, right? So I can replace x prime with x. Previously, we were reserving, or Sakurai was reserving x for an operator and x prime for a number. Here, everything is in terms of functions. So, in case you were wondering, differential operators, differentiations, are like the infinite dimensional versions or continuous limits of matrices. Right? That's what it means. All right, so what is this? This is a partial differential equation, a PDE. We want to solve this equation, right? In simple harmonic oscillator, we solve these equations, but we got away with this algebraic trick of creation and annihilation operators, right? It's equivalent to solving this equation. And I'm sure in your quantum mechanics courses you've taken before, if in your undergraduate level courses, you have looked at solutions of this. But so we're not going to go over solving many examples of this. You've seen some of it. But I want to say a few important things. Like any differential equation, PDE, you need boundary conditions to solve it, right? You need boundary conditions. Where are the boundary conditions? What are the boundary conditions? So let's discuss that because it's important. What goes into this equation is the only thing that goes into this equation is a known potential that somebody has to describe to me as a function of space, and then some energies E that I'm hopefully going to solve for, and the wave function. It's like an eigenvalue problem, right? An eigensystem problem. But I have to prescribe some boundary conditions. What are the boundary conditions? The boundary conditions are how the wave function behaves out at infinity. Now, let's try to see what are the choices. One choice that you might have been using without knowing is the choice of a confined particle. So here's V of x. V has a dimensionality of energy, right? So I can ask, what is the energy of the particle compared to V of x? If the energy of the particle is below, if the energy of the particle is below the value of the potential out at infinity, right? The particle is confined. Think about the harmonic oscillator, right? Like classical physics. If your particle is rotating around here or moving around, but it has just enough energy, when its whole energy is turned into potential energy, it reaches this point, it can never make it out to infinity. Because the potential energy out at infinity is more than what the classical particle has, right? So this particle is stuck in the middle. That's why it's confined. And because they interpret, so let's talk about these particles, confined particles. Because the interpretation of the wave function squared is probability of finding the particle, for a confined particle, you would like to say that the probability of finding the particle out at infinity is 0. That justifies the boundary condition, BC's boundary condition of British Columbia. The limit of the wave function as you go to out to infinity is 0 for a confined particle. Does this make sense? This is as opposed to a particle that has more energy. What is the physics of a particle that has more energy? It will make it out, right? It will make it out. Now, one thing just to remember. So this is classical physics, right? Now, I drew this in a nice way. If I have a particle here, classically, it will get stuck here because there's a bump here. It cannot get past that bump, right? In quantum mechanics, there is a non-zero tunneling amplitude for it to go from here to here, right? So it can cross a barrier, and but it pays the probability pays a cost for how far this thing is and how high it is. It can never tunnel to infinity because infinity is infinitely far away, and there's nowhere to tunnel to, right? It can tunnel to somewhere where it has enough energy to exist, right? So there's no such a thing. But so the distinction between for a confined particle, the distinction between quantum and classical is about where the particle is living, right? In classical situations, it's either living here or here. Quantum mechanically could be in a superposition of them, and it is in a superposition of them, always generically, right? But out at infinity, everything is possible. One lesson for the rest of your life in physics. When we start quantum mechanics in an infinite medium, we absolutely always have to make the behavior of the particle or system classical at infinity. You simply cannot allow the particle to fluctuate quantum mechanically at infinity. This has dramatic consequences for, say, quantum field theory, gravity, all of that. It's a key principle over there. But anyway, just coming from the fact that I just want to point out here, just remember that out at infinity, if the particle doesn't have enough energy to make it, the potential is high. Classically, you don't expect it to be there, and quantum mechanically, it won't be there, right? Good. This is what a confined particle is. What is a non-confined particle classically? Is some ball that has enough energy up here. It comes and goes through a bunch of bumps and passes through. It's like a car going through a bunch of bumps on a road, right? Now you could bring a particle out from infinity here, out from infinity here. They have more energy than the potential. They collide and go back to two cars collide and go back. That's the description of what we do in particle physics, right? Scattered. So with non-confined particles, the physics often involves scattering. All right. So an idealization of this setup is if you want to make sure that, so now you have, so they have two types of particles, confined particles and non-confined particles. Sometimes for the reason I just said, non-confined particles are called scattering states, right? If you want to make sure that all your particles are confined, one way to make sure that's true is to sit an infinite potential well, right? You said my potential out at infinity is infinite. Even better. So simple harmonic oscillator does that. Make sure that there's no way for a simple harmonic oscillator to have a scattering state, right? Things cannot go up. So all this wave function we found is all that there is, right? But a very extreme idealization is this infinite potential well, right? All right. Now, here is an important step. Quantization, quantum numbers. Quantum physics is all about integers, a bunch of solutions being allowed and nothing in between, right? Remember the spinner had h bar over 2 minus h bar over 2 and nothing in between, a behavior you do not expect for a vector. Here, quantization comes from the fact that for confined particle, when you solve the differential equation, this differential equation with energy E less than V of X, only discrete values of E are allowed. It's a fact about differential equations. Quantization comes out of a fact about differential equations. Now, we're going to see that in a bit. This only applies for confined particles. not for scattering state. Scattering state can have any energy. Is that clear? Do you know an example of a state solution to Schrodinger equation where it's a scattering state and things are like you have energy more than the potential out at infinity and there's no quantization? You have an example of that? Yeah. Plane wave, exactly. If you want to make sure that you have enough energy out at infinity, set the potential to zero everywhere, right? What's your Schrodinger equation? It's a trivial equation. Del T psi of x and t is minus h bar over 2 nabla of h psi. What is this equation called? It's called the wave equation. What are its solution? Plane waves. The energy of plane waves is not restricted. These are legitimate solutions of quantum mechanics. There is no quantization to be found, right? Any energy is allowed. So quantization is intimately tied to confined state. We don't call them confined particles. The solution is called bound states. That's what it's called. Bound states. What are examples of bound states? We're all made out of bound states, by the way. All molecules are bound states, right? So they're made out of a bunch of atoms. These atoms are stuck together. They can't make it out to infinity. So that's a bound state. What is the potential? The interaction between the atoms. Right? These are bound states. Otherwise, it would be just boring hydrogen. The universe was boring. He was back in the days. All right, so that's what it is, and that's the example of waves. What I'm going to say today, hopefully, well, I might actually make it today, is going to be about precisely the comparison between states that are bound and these plane waves. So one thing that you realize is that if you're discussing plane waves, because there's no quantization principle, you still have Schrodinger equation. It's more likely that you could connect it to classical physics. We're going to do that, actually. Bound states are very quantum. They're deeply quantum. They're hard to make sense of classically, right? Your intuition just falls apart, as we saw in energy eigenkets. They do not behave the way you would expect classically, right? But we're going to see that these states that are not bound, plane wave physics, that's exactly the intuition you should have. Plane wave physics comes pretty darn close to classical physics. And we're going to actually see the connection and how it's called the classical limit. We're going to discuss that in the context of what is called a WKB approximation. That's going to be a big part of today's lecture. Any questions? Am I recording? Oh, yeah. So is it clear that where this quantization comes from in this wave mechanics? It comes from the fact that you want bound states and you have a differential equation to solve. If you're wondering why that's, oh, by the way, in this case, what are the bound states? It's just harmonic modes that should have nodes here. The wave function should have, these are cosine and sines, the solutions of this. They should have nodes here. So here's one, here's one. Next one is whatever, I cannot draw it. But you see the analogy with this picture. These guys don't have a node of distance away because the potential is just like kind of this x squared. If the potential was just shooting up to infinity at some point, it had to have a node. This is quantized. I've learned that when I zoom in and out, Zoom has a delay, has a lag, and it's kind of irritating for people who watch it. Yeah. Yeah. Yes. Yeah. Well, no, they have a bunch of states that are bound, and a bunch of states that are not bound. Well, here's a yeah. Is that good? That's consistent. In fact, even if you don't have finite well, you have some potential. Generically, it's the case that doesn't go to infinity. If the potential out at infinity doesn't go, like, think of instead of x squared, take a potential that looks like this, right? Then you generically have, if you have energy less than this, you have bound states. They're called molecules. Out here, you might have just scattering states. It's possible, like if you take a molecule and give it a lot of energy, or like heat it up, at some point it will fall apart. It will break down, right? Those are a lot of events. A lot of chemistry is all about molecules falling apart. That's what's happening. You go from one solution here to another solution up there because you give it enough energy. Good. That's where chemistry comes in. Okay, I'm not going to be an arrogant, annoying person. All right. Now what we're going to talk about is interpretation of wave function. So there's some cautionary statement I should make. You got to be very, very careful. Everything we say here is mathematically correct. A lot of these interpretations are for you guys to think about and keep in mind. And some of them will give you some methods to, given a solution, come up with some physics interpretation of it. But be careful, because interpretation is a slippery business with quantum mechanics, okay? So, all right. The only thing that we're going to take as factual in quantum mechanics is that the wave function squared is the probability for an event, right? That's called, does everyone know what the name of that is? Born rule. As a matter of fact, we learned very, very recently that, I learned very recently, I think the community learned very recently, that there is a simple way to derive Born rules from basics. Born just, when Born said it, it was wacky, but it just matched the experiments. Now we have some sort of derivation of some more basic principles, but that's not the conversation that we're having here. Okay, so if you have a continuous variable, when you do not have discrete outcomes, you have continuous outcomes. What replaces probabilities are probability densities, right? So for example, if you have a particle that could be anywhere, the probability for it to be dx away from x naught, some small ball of radius dx around x naught, is just the probability density times the volume of that ball. Good? That's what the meaning of probability density is. Now, imagine a ball like that in space, right? If it helps, think of it to be one-dimensional. I think it does help. X, and I'm going to plot here psi squared of x, right? So let's say you have a wave function that looks something like this. Squared of it looks like this. The probability to find a particle from here in between some x naught, between some x naught minus d of x and x naught plus d of x, is this integral down here. And if it's infinitesimal, it's just the value of rho. This is rho of x times d of x. 2d of x. All right? Good? Everybody's with me? Now, conservation of probabilities must hold. What does that tell you about the probability of the particle being in this point? As the wave function evolves, you could think of this as liquid, right? This can go up and down, right? But the fact that the whole amount of liquid in a tank is fixed tells you that if I take this region, the amount of probability current that comes in and the amount that goes out, if you subtract them, that should be the total change in the probability density. Right? That's continuity equation for liquids, but here there will be a continuity equation for rho. That's sensible, right? Good? what would that equation look like? It would say that the change in the probability density, has to be the gradient of this flux. This is flux. Good. So probabilities should come from somewhere. You can't just increase the probability of here and not pay a penalty somewhere else. That should, probability somewhere should go down, right? That's conservation of probabilities. Now, the analogy between a tank of water and this rho will suggest that there should exist a notion of probability current or probability flux, the same way that water has a notion of flux. And this notion of flux, if you just take the Schrodinger equation, you could show it's a one-liner, maybe two-liner, that this is the flux. How do you show that this is the flux? How do you find this equation? How do you solve for this? How do you find what J is? What is rho? So what should I calculate? I should calculate this, right? How do I calculate that? Well, this is del T of psi star psi. What does Schrodinger equation tell me? What del T of psi is? It also tells me what del T of psi star is by complex conjugation. So I can just plug in the Schrodinger equation into this and find the right-hand side. Good? What is the right-hand side you find? This equation. This is what we're going to call probability flux, okay? And what I'm going to do in the next few minutes is describe some physics intuition. But let's say if everyone understands where this comes from. It has a very, very weird, interesting, semi-classical interpretation, okay? Good? So what is the flux? What happens when the flux is large? Let's say the flux coming in is large. Probability shoots up really fast, right? So the fact that it shoots up really fast, it suggests that it's in the same way that it actually continuity equation, if you recall, in classical physics for this. Oh my God, I can't talk. For tank of water, as J is rho v, velocity, right? The flux in classical physics is density times velocity. So this suggests that if you take J divided by rho, it gives you a notion of quantum notion similar to classical velocity. Just keep that in mind. That's going to be what we're going to be working with for the rest of this lecture, but it's not to be taken literally. Quantum mechanically, if we do all these calculations, this is all legit. What the interpretation that you put on it is just for you to get used to these things. These are not like, so that you have some meaning associated with this. So is the idea clear? There is a notion of flux, and flux, and at least for a tank of water, has to do with the density times velocity. So there is a notion of velocity appearing somewhere. But this is not actual part of it. Yes. It's I what?
I something very well.
Imaginary. Yes, I am is imaginary. So yeah. So if you have a complex number, you just separate the imaginary part. Thanks for asking those things. Sometimes I write notation that I don't explain. Thanks. Yeah.
Not J or
Low V, low T. Where is that?
the company equation.
Yeah.
Is it,
Oh yeah. Sorry. Yeah. Okay. I'm being a little bit sloppy with my vector calculus notation. That would be dot divergence, just by the virtue. Yeah, up to. Yeah. If you put a gun next to my head, I'll get all the indices right. All right. Yeah, I actually had it. Dot. That's divergence. there is a very obvious way of figuring out what should be there. But anyway, that requires a little bit maybe more representation theory. But anyway, all right. So this is a probability flux, and then there is a notion. But I want to insist there is no actual velocity. It's something that you could define that resembles velocity quantum mechanics. One more thing to know is, all right, is that good? So you could ask, what do I get if I integrate the flux over the whole space? You get the expectation value of momentum divided by m. It has the right dimensionality, right? So if you integrate this flux over the whole space, you find velocity over m. And this is intuitive. Hopefully. Does anyone know why I say it's intuitive? Well, okay, think about it. I'm not gonna force it. All right. So this is an exact equation in quantum mechanics. Right? The right-hand side, when I write expectation value of P, hopefully you know that that is a bracket, right? That's the bracket psi P psi, right? That's how the left-hand side and right-hand side are related. All right. So that sounds good. It seems like there is a part of the norm of the wave function that we could associate some sort of a classical looking interpretation to. But you got to be very careful because there's more to a wave function than it's just norm. What else is there? It's phase. It's all about the phase, actually. It's all about the phase. So because wave function is a complex function, I can always write it as a square root of its norm multiplied by phase that I'm gonna write suggestively as I s over h, where s is a real number because it's a phase. We're gonna find a natural interpretation for s, right? So far what we've been doing, what we focus on was rho, some sort of interpretation for rho. We're gonna come up with an interpretation for s, and this step of the way is super deep. This part was sort of intuitive. This step is a little bit deep, and it requires a little bit more doing some reviewing of your classical physics. All right, is this clear what I'm doing? I never asked for questions from online people, but I'm imagining if they have questions to come to class, what they would ask, they would speak up. All right. So now what we're going to be after is we're going to be after an interpretation for the phase of the wave function. Does anyone know where this is going? What is S going to be? I gave it a suggestive name, S. So what was the probability flux? The probability flux was imaginary of psi star nabla psi h bar over m. So let's plug in this expression inside, and then you find that the probability flux is rho over m nabla of s. Sorry, rho over m nabla of s. Like, yeah, gradient. The left-hand side is a vector. This is also a vector. So what did we find? We found that in our continuity equation, this flux that we found has to do with the variation of the phase over space, right? How quickly the phase varies in space tells you about the flux. probability flux. This step, I admit, is hard to interpret, but these are facts, right? But let's try to make it a little bit nicer. Question? Is it clear what I'm doing? So the imaginary and the real part of the wave function, the evolution of the imaginary and the real part of the wave functions are related, and the continued equation precisely does that for you. It tells you the derivative of the norm of the wave function is controlled by divergence of the gradient of the phase. That's what it says. Good. So let's just make sure that we follow this. What if I have a plane wave? A lot of our intuition comes from a plane wave. If I have a plane wave, that's the solution. What is the gradient of the phase? So the phase is that S for plane wave is simply that is px minus et. That's what S is, right? So the gradient of S is p. So what you end up with for plane wave is del rho del t plus nabla divergence of rho p over m. Very good, right? This is literally velocity that we have. For plane wave, things hold literally. You literally have a continued equation with velocity actually sitting there. Good. So now you see why the imaginary part of the phase is related to velocity. Well, you knew that for plane waves, that was the case, right? Good. Any questions about this? Yeah.
There's only two roads.
Yes.
And we have a last one.
Yes.
Partial road.
P is momentum. Yes.
Yeah.
So del T of rho plus nabla of rho P over M. Yes. All right. So very good. Now what we're going to discuss. So we give an interpretation for the real part and imaginary part, but the imaginary part wasn't really an interpretation. I have to tell you a little bit more about that to make it cleaner. What I'm going to do is if Schrodinger, so here's what we're going to do for the rest of this lecture. I think I'm not going to make it to the end of it, but here's a question. If Schrodinger equation is describing the physics of a quantum system, and we say that the quantum phenomena are controlled by h bar, there should be a sensible limit of h bar going to 0 that gives you classical physics. That's what we're going to try to do. That limit is not clear. It's not obvious from Schrodinger equation, because if you send h bar to 0 in the Schrodinger equation, the time derivative disappears. You can't do that. Good. So we're going to describe, this is actually a very nuanced discussion. We're going to try to derive, at this point you should also be complaining. H bar is dimensional. So what the hell are you talking about? What does it mean to say H bar is small? That's what, so to deal with this properly, that's what we have to actually understand. What is the variable that must be small? What quantum systems show classical behavior? That's another way of saying that if I look out around me, why do I not see superpositions? It's basically the same question. The answer to which is, in its entirety, is unknown. Parts of it we understand. In 2024, we do not understand why the world looks classical. This is a fact. We understand certain aspects of it. And some aspects of it are simple enough that I can explain this course. All right. So to do that, we start with this splitting of the wave functions into its real and phase part, into its norm and phase part. This was our Schrodinger equation. I'm going to plug in this equation inside the Schrodinger equation. So I get this two line. of equation. This is the left-hand side. This is the, sorry, this is the right-hand side, right? The time derivative part. And this is the left-hand side. The left-hand side, the nabla piece comes from, so where is the V? The first line has to do with the first term here. And then the V is just this. I've removed an overall factor of phase. Right? So the first line is just the momentum piece. The V is this term, and the right-hand side is this. Good? Now, let's go through this term by term and see, naively speaking, what orders of H bar they are. The first term is order H bar squared. Next term is order H bar. So if there is a sense to send H bar to 0, this is not dominant. Next term is order 1. Good. So if there is a sense of sending H bar to 0, this term would have to be classical because there's an H bar sitting outside, right? These two terms are deeply quantum, are quantum mechanical. This term is also order H bar. So from the kinetic piece, there's only one term that looks classical looking. The potential has no H bar in it. So that's order 1. That's good. From the right-hand side, there are two terms. The first term has an H bar. The second term does not. So suppose H bar is small. Naively, it would mean that I would be collecting these three terms that have underlined, right? Good. So that's the equation I have to consider and drop all the other terms. But what exactly am I saying when I say H bar is small? H bar is dimensionful. What I'm saying is this. Oops. Uh-oh. Sorry. Here. Something happened. Oh yeah, we're good. This is the approximation I'm using to get rid of these terms and only keep the terms that have underlined with this orange beige color. We'll describe the physics of this approximation. It's very, very important because it gives you some piece that why the world looks like the way it is. It does. Can anyone already tell what this condition is? So it says H bar is much smaller than del of S squared over the del second derivative of S. Can you already see the physics of that? Yeah. The opposite. It's wild. Because H bar is smaller than that. So okay, well, I'll elaborate that. It just means that the phase is oscillating really rapidly. This is what you expect as well, because you expect macroscopic stuff to have a lot of energy, right? If a quantum of energy is H bar omega, you expect a macroscopic for a single photon or single particle, right? Like a quantum particle. You expect an Avogadro number of particles. So the amount of energy, total energy that you have is much, much larger than H bar omega. That's not literally what the expression is. The expression is that the total action, energy times time, is much larger than H bar, because that is the fair dimension comparison. So when energies are large, things oscillate insanely fast. And then they look classical. Maybe it's counterintuitive in a sense, but things that oscillate really, really fast in their phases, wave function oscillate really, really fast, look classical. Any questions? Actually, constructing a system that behaves very quantum mechanically, which is a challenge these days for quantum computing, involves things that oscillate very slowly, building things that the phase oscillates very slowly. All right. So let's keep the terms that I underlined. I was underlining, and here's what it is. So I'm going to put order h bar here, meaning that I'm dropping those terms, the other terms, so that I can write an equation. Does anyone recognize this equation? If I set the order h bar to 0, this is classical physics. It's a formulation of classical physics called the Hamilton-Jacobi equation. I'm going to explain that, or hopefully remind you. I don't know if you, how many of you guys have seen Hamilton-Jacobi equations? 1%, 2. Unfortunately, I won't have time to teach it. I'll just give you some hints from the things you have seen before. Okay? But this, so let me drop this term, cross this term. This equation being equal to 0 is equal to F equal ma. It's a reformulation of F equal ma. And that in that reformulation, S function has a name. Anyone? Action. Action. Action has also the same dimensionality as h bar. So that's good. Right? All right. I'm gonna very quickly make sense of this equation. So what is this equation? This equation, bring this term to the right-hand side. It says del T of S is the Hamiltonian. So what is the Hamiltonian? Hamiltonian is P squared over 2m plus V of x. Here's V of x, and I evaluate H as x, setting P equal to del S. Right? Is this clear that this is just the Hamiltonian on the left-hand side? Evaluate it. So this equation down here, this equation is a rewriting of this equation. So I'll explain this equation. This is called the Hamilton-Jacobi equation. It's the same thing as F equal ma. You've seen already the Hamilton equations, right? Good. I have one slide about this. I'm going to try to do it on the board. All right. So the goal is to derive this equation. The time derivative of the action is minus h. What is the action? The action is the time integral of the Lagrangian. Right? And Lagrangian is a function of x and x dot. So if you take the total derivative dt of s, you're going to get del s del t plus del s del x x dot. Right? Because function s action is a function of x of t and t. Right? Hopefully that's clear. But then also this expression tells you that this is nothing but the Lagrange. So I can rewrite this equation, writing del t of s is Lagrangian minus del s del x of x dot. Good? I claim this is nothing but minus h. Why? Because h is px dot minus l. All I need to show is that del s del x is p. But that's just something you could easily see from your classical physics. If you find yourself confused about these few lines, plug in the Lagrangian of a massive particle and a potential. What is the Lagrangian of a massive particle and potential? classical physics. It's half m x dot squared, right? Minus v of x. Good. What is the Hamiltonian of this classical particle? That's half m, p squared over 2m plus v of x. What is this equation I'm writing? H is px dot minus h. H is px dot minus L. Check those equations. Take derivatives. Do all these derivatives that I'm describing here, and it'll all work out. It's a reformulation of F equal M. Good. So we took. Let me remind you what we did. We took the Schrodinger time-dependent Schrodinger equation. I took the wave function, wrote it as some. It's square root of rho, which is this real part. It's the norm of it, multiplied by a phase. I gave that phase a name that was suggestive, S. Plugged it into the Schrodinger equation and dropped the terms that were h bar suppressed. What I found was the Hamilton-Jacobi equation with the phase of the wave function becoming the action of the classical part. This is very deep, actually. Any questions about this? I would rather explain this a little bit more than just start given the amount of time we have. I have one more point to actually finish. Are there any questions about this, right? So what we did was, at least for this simple limited discussion that we're having here, we showed that quantum physics, Schrodinger equation, quantum physics is not completely unrelated to classical physics. It's related. It actually does give you classical physics up to this approximation. Now I have to justify what this approximation is. That's going to be the rest of this lecture and a little bit of the next lecture. Good? All right. Are there any questions? I think it's good if you guys ask questions. A huge caveat. Well, sorry, not caveat. Why do I say that? Why is this not convincing enough that classical world comes out of quantum mechanics in this limit? If I give you a nice interpretation of this smallness of h bar limit, what is left to do when I say in 2024 we still do not understand how classical physics comes about? What did we do? We started with a ket, right? Wave functions. These were pure states, and pure states had superpositions, right? And those were the quantum phenomena that we didn't have classically. This explains why we do not see superpositions in class around us, classical world. But there is more to quantum mechanics than superpositions. We'll see that in axiom 4 of quantum mechanics. We haven't gotten there yet. There's a phenomenon called entanglement, which is not superpositions. It's a brand new phenomenon. This explains how we get to the phases. No, sorry, not phases, superpositions. But we're not done yet. And that aspect of it is not fully understood, it's partially understood. Okay? So when we're talking about pure states and their Heisenberg equation, this argument and this discussion is rather satisfactory. But there's more to quantum mechanics because we have only gone over 2-3 of the axioms. I don't remember how I was counting. We haven't discussed it yet, but we'll get there. We'll talk about this. All right. So what is this approximation? Now, to make progress, how am I doing on? Oh, okay, no, I have only two. But to make progress, I'm gonna focus on a special class of states, KEPs. These are going to be the stationary states, otherwise known as the eigenstates of energy. Why? Because their time dependence is very, very simple. Everything I said before was general. These guys have very simple time dependence. It's just the wave function is multiplied by e to the power minus I et over hy. Right? So what does this tell you about the action, the phase of these wave functions? That S, mysterious sounding S, was nothing but S et for these states. Good? So, sorry, no, that was a lot. It's et up to a constant that's time independent. Because what I found was that del T of S was this, I fixed it, right? So this tells you that for these stationary states, the action could be split into two terms. A function which is only x dependent minus et. This is specific to stationary states. I cannot stress this enough. This would be completely wrong if you try to do this for a general state. That's incorrect. It doesn't happen. All right. In classical physics, this function also has a name. It's called the Hamilton's characteristic function, in case you're wondering, in case you care. Now, what is the interpretation? When you have a wave, the surface of when you have a wave propagating some medium, you have a phase. And the propagation is described as the surface of constant phase that's called wave front, moving forward as a function of time. That's what it means for a wave to propagate in space. Good? Surface of constant phase is moving in space. Here, what we're finding is that for these states, time evolution, the word wavefront is replaced by surface of constant S. The surface of constant S is propagating in time like a wave would. Just advances in time. And the particle trajectory is simply normal to this wavefront, as you would expect from a plane wave. Right? So unfortunately, I ran out of time, so I won't have time to go over justifying that approximation. That will have to wait for the next lecture. But let me just summarize and answer questions. So what did we do today? Actually, I don't remember what we did today. I reviewed stuff. Oh, we talked about coherent states. These are the eigenkets of the annihilation operator. We said they satisfy minimum uncertainty. We wrote down the wave mechanics time-dependent equation, Schrodinger equation. We talked about the boundary conditions for this, right? How you have two types of solution potentially. Confined particles, these are the setups where you have less energy than the potential value of the potential at infinity. So these are bound states, or you have more energy and things can propagate, make it all the way to infinity, right? It's only the confined particles or bound states that have discrete energies, right? That's important. We talked about the interpretation of the wave function. As a complex function, we took out its we wrote it as a real number multiplied by a phase. We interpreted the real number squared, right, as a probability density, which naturally led to the idea of probability flux because of conservation of probability, which also hinted at some notion of momentum and velocity. But this is a slippery business. You don't want to take that literally, okay? Then we talked about the phase part and the physical significance of the phase part. To make this very clear, what we did was we took the Schrodinger equation, expanded in H bar, and showed that the phase is basically related to the action, classical action, in the limit of H bar equals 0. This was Hamilton-Jacobi equations. All right, this was a summary of this lecture. Are there any questions? All right, if not, thank you so much, and I'll post the new homework.